Okay. So what I am going to talk about today is a work in progress with Alexei Borodin, who is now in Caltech. And all that started when we were looking with him on lozenge tilings of the plane. This is an area which saw very spectacular progress in recent years, starting with works by Richard Kenyon, and then many people were working in that. And very recently, Andrei Okunkov got his Fields Medal on things which are included in this topic. So lozenge tilings are those things that you see on that picture, and also you can think about them as planar partitions of integers. Well, I am working in statistical mechanics, so I have I almost never talk to combinatoric people, but the subject is very nice, and so as an introduction, I just want to repeat some probably well-known facts about plane partitions, which are very fascinating subject to me, and probably you know those things better than me. This is very little to do with the main body of my talk, but still let me just put them on screen for you to appreciate those nice objects once more. So let me first just tell you a few things you know better than me. So first I want to talk about just ordinary partitions of integers into integers, but for the reason which would be clear soon, I want to call those integer partitions as brick partitions. So imagine I have a box like that, and there are written in some integers and zeros, as you see, and then we can read this as number of bricks of various lengths. So we have 2 of length 2, 3 of the length 3, 1 of length 5, and 1 of length 6. And we take those bricks, and then we can arrange them into Young tableau. So I put 2 of length 2, then 3 of length 3, then 1 5, 1 6, and this makes a partition of an integer. You should just count how many cells we have here. And then one might ask, what is the generating function of the sequence of the number of partitions of an integer into well, what is the number of partitions of a given integer? How many Young diagrams are there which have n cells? And it is easy to see that this sequence is given by this generating function. This is everyone knows, and that's a very nice thing, and it's easy to see. Now let us talk about something else, which I call hook partitions of integers. I cook up myself that name, but maybe something else. It may be another name for that is known. And what that is that now we have a rectangular box, and again we put some integers into that. Zeros are not listed, others are listed here. And then we now interpret every box as a hook. And here is this hook correspondence to that table here. So we have 2 objects of length 1, see those 2. Then we have 2 hooks with 4 cells, right? Then we have 1 with 5, 1 with 4, and we have 2 which correspond to these 2. And if you add the number of cells in those hooks you find 35. So this what you see on the screen, we would call it as partition of the integer 35 into 8 hooks. Okay. And then again, it is easy to write down the generating function of the number of hook partitions of an integer. And this is given by this expression, and this is straightforward. As straightforward as to write down the generating function of the usual partitions. Okay, what is much more striking about this relation is that at the same time this very formula gives also the number of planar partitions of an integer. Well, planar partition is something that I showed on my very first slide. Okay, so this is one of the most known achievements of McMahon, as I understand. Okay, and it would be nice to really to be able to take those hooks, to think about them as objects made from unit cubes, right? And then to assemble the collection of hooks into a mausoleum. And unfortunately, this cannot be done just like that. But it can almost be done. What you have to do, unfortunately, you cannot just use those solid hooks to build your skyscraper, this partition. What you have to do, you should take every hook and you should cut it in 2 pieces like this, and then you rearrange those bricks, which are of half integer volume each, and you can rearrange them in such a way. It is a very clever construction. This goes under the name of Robinson-Schenstodt-Knut correspondence. But the fact is that you can rearrange those things and to build a skyscraper from them, and it is a one-to-one correspondence. And so this is this very fascinating fact, and it's, to me, it looks like a miracle that McMahon was able to write down a formula which somehow has inside it this Robinson-Schenstodt-Knut correspondence. So apparently he was not aware of that. But anyway, this is again a fact. And then one can go further. One can think about what I would call tripod partition. You just take a three-dimensional body, a three-dimensional table, and you put integers into that, and then you consider those hooks with 3 legs, if you want, or such objects. And again, you ask how many ways are there to partition an integer into tripod, and as before, it is easy to find that this is the formula which you would get, and then you can just compute things, and you will find that sequence of how many partitions are there for the integer to be written as a sum of the various tripods. So this is for 0, this is for 1, this is for 2, and so on. Very good. And for some time, as I heard, McMahon believed that this is exactly the generating function of the solid partitions. That is those 4-dimensional skyscrapers with the given volume, and but it is not the case, unfortunately. And so this is the numbers of how many solid partitions are there, again for the integer n. And as you see, the 2 sequences are starting very much in a similar way, but then they start to diverge. And okay, and my understanding is that well, this is a quotation from somewhere, that this sequence is still there is no good way of understanding what's the nature of it, and write down a generating function for that. Okay, so this is still an open problem and very nice problem. So I think a little bit about this once and again. So it seems that there is no good formula for the solid partition, for the generating function of the solid partition. However, if you ask yourself a bit more modest question about how many partitions are there which have a base which is a box A of the size ABC, then you can write down such a generating function, and it turns out to be a polynomial which depends on those three numbers, ABC, times this infinite product. And this is not hard to write down, so at least there is, so you can compute using that formula some, well, you can find some answers to the solid partition question, but the general formula apparently is missing. Okay, and this is all I wanted to say. As I said, I like to talk about those things, but I have not often occasion to discuss them. And okay, and now I go to the main subject of my talk, which is the connection between some Gibbs random fields and some determinantal random fields. And the first connection that we were able to make is exactly this random field corresponding to lozenge tilings. Okay. Okay. So on that screen, I just remind you basic things about Gibbs random fields. So what you do, this is the example of the Ising model which you were talking about the other day. So you have, say, a lattice. Let us talk about, say, two-dimensional lattice. And then we have spin variables which are taking values plus and minus 1. And this is sum of the nearest neighbors. And this is a formal, what is called a formal Hamiltonian. And once we have this formal Hamiltonian, we can talk about Gibbs random fields corresponding to that formal Hamiltonian and to some inverse temperature. And we do it in the following way. We take a box, lambda, and we fix some configuration of spins outside that lambda. And then again, we write down now not a formal energy, but just the energy. This is a finite sum now. So this is the energy of a configuration in the box lambda, given the boundary condition psi outside that box. And then we write down the partition function, which is just the sum of those exponents of this energy. And then we define a conditional distribution of the measure, which the conditional distribution of let us consider that collection of conditional distributions. So for every box lambda and for every boundary condition outside that box, we have a probability distribution. And then we say that a measure mu is a Gibbs measure with that corresponding to that Hamiltonian if the conditional distributions of that measure are given by this formula. Okay? So the formula is easy to write, but then there is a question how the corresponding measure of which this formula gives you conditional distributions is looking. And this is something hard, something, well, you just have some qualitative theory about that, and very rarely you know very explicit what are the correlation functions and things like that. Okay, so those are generalities about Gibbs random fields. On the other hand, determinantal random fields are random fields for which the correlation function is something easy to write down, while the conditional distributions sometimes are very hard to obtain. So what are the determinantal random fields? So let me again talk about, say, two-dimensional lattice, and I consider a random field on that lattice which takes values 0 and 1. And then I have to specify what are the probabilities of some unconditional probabilities of some events. I have here a couple of ones and there a couple of zeros, and I want to know what is the probability of that. And in fact, it's enough just to say what is the probability having at a certain I take a finite set of sides and I put ones there, and I want to know what is the probability of that. And I say that my random field is determinantal random field if the following is true: if there is some matrix K K, this is a matrix with matrix elements indexed by pairs of lattice sides. So for every 2 lattice sides, I have a number, and this is a matrix. And then if I want to compute the correlation function, I want to know what is the probability that all n ti's are 1 on that finite set of indices. What I have to do, I should build if that set, say, has L points here, I should write down this L by L matrix, and I should take a determinant. And if it so happens that all those probabilities are given by those determinants, then I call my random field determinantal random field. Okay. In general, the examples that the humankind knows, those examples are such that this kernel, this function of 2 variables, 2 lattice variables, actually is a complex valued function. So see, and yet all those numbers have to be real numbers between 0 and 1. Whether that happens or not, well, this apparently should not be that easy to understand. Anyway, such the rationale behind giving that definition is the fact that such objects do exist. And you find many of those in the random matrix theory, though they are determinantal process, one-dimensional random determinantal processes. And I'm going to talk about 2-dimensional lattice determinantal processes, but such objects also exist. Okay.
There must be some property of the matrix.
Definitely, because on the left-hand side, this is a probability. Yes. That's what I'm saying. Yes. So, definitely, almost you take arbitrary matrix and it almost never works. So yeah, sure. So it's a miracle. So it is that same kind of a miracle as you would find in exactly solvable models of statistical mechanics. So it's very rare that those things happen, but still they happen, and there are examples. And okay, so this is what the determinantal random field is. See, in that situation, to compute, if this is already the case, if you are told that your random field is determinantal, and you are given the determinant, the matrix that describes it, then it's very easy to compute the correlation functions, right? But to compute, say, conditional distributions might be very hard, because that again requires to take a limit. So what we wanted to understand is whether we can have both properties, whether there are nice natural random fields which have both the Gibbs property, that the conditional distributions are easily computable once you take a box and you fix the boundary condition, and on the top of it, the correlation functions are given by some determinants. Okay, and yes, the first example, which is exactly this lozenge tiling problem, gives us such this is the case exactly. That from the point of view of the Gibbs fields, the Gibbs description of the lozenge tilings is even maybe too simple, but still it is like that. So you have to tile your plane with three kinds of rhombi, and you take a box and you fix everything outside. Then what you have inside is just a uniform distribution on all possible tilings of that box inside. So this is so you're saying that the conditional distribution is just uniform on all allowed configurations. So in that sense, this is, of course, you can say that this is a Gibbs description of that field. On the other hand, it is also possible to write down a kernel which makes that random field into a determinantal random field. And here you see that kernel. And as you see, this is a complex valued kernel. In that case, the kernel is actually translation invariant, so it just depends on the difference of those two lattice sides. And it is given by this formula. So you have to compute for every vector with coordinates k and l at integers. So k, the pair is a vector, or two-dimensional vector on a lattice, and you have to compute this integral. And those are and this is the kernel which describes your this random field of lozenges on the plane. Now,
Z is just a parameter?
And Z is a parameter, and a very important parameter, because if you think about those lozenge tilings, you will find that there is a phase transition there, so to say. There are many different random fields which correspond to the lozenge tiling. Namely, if you look at this lozenge tiling and you adjust your eyesight, you can think about it as a surface, right? It is a surface in three-dimensional space, spanned by these unit squares of a three-dimensional lattice, and that surface has asymptotic tilt. Okay, so asymptotic tilt is a two-dimensional, is a unit three-dimensional vector, which means that it is two-dimensional. The parameter is two-dimensional, and this z, this complex number, is also this, and this is that two-dimensional parameter which takes care of various random fields made from lozenges that correspond to different tilts of the surface, of the random surface. Exactly how that works, exactly how the correspondence now let me just make it a little bit more precise what I am saying. So imagine we have this tiling of the plane, so you should ignore those things. Imagine this is an infinite tiling, and then I should choose one of the three directions of those lozenges. So let me take those horizontal, I would call them, and I then just fix those three, and I want to know what is the probability that I will see a horizontal lozenge in those horizontal rhombus at those three locations. That has a probability, and this probability can be computed by using that kernel that I put on the blackboard, on the screen. Okay, so in other words, the random field of the positions where I put ones where I have the rhombus horizontal, and I put 0 here in all other places. And those ones and zeros, they form the random field. And the ones, the probability of seeing ones, are given by this kernel that I showed you before. But my title is just a second. Yes, yes. Um, okay. So the question we wanted to answer with the Borodin is the following, which I cannot put formally, and informally it is how on earth that kernel knows that the field it describes is a Gibbs random field. How come that the boundary, that you fix the configuration only at the boundary and you know the probabilities inside. And the answer that we got for that random, for this for the case of lozenge tilings is the following. The reason for that lies in the fact that there is some simple linear relation between the matrix elements of the kernel that I showed you. So, well, it turns that if you know the following, that you have some kernel, and somebody already told you that that kernel defines for you probability distribution. So it's really defines a determinantal process. And moreover, you check that this the kernel satisfies, well, some kind of linear relation. I will give you more. I will talk about other examples later. Then those two facts together tells you that the underlying random field has some kind of the Gibbs property. So this linear relation is the reason why things are so nicely looking. And exactly what is looking nicely are those ensembles of non-intersecting walks, and this ensemble you are getting if instead of those horizontal plaquettes, you consider the family of all vertical plaquettes. And then, as you see, they are making paths. And if you interpret your determinantal random field as a measure on those paths, then you find that those paths are really behaving in a manner which is very similar to the Gibbs random fields, and I'm going to explain that now. So let me define for you what is it that I will call Gibbs random path ensemble. Maybe let me go to the picture, and then we go back to this slide. So imagine I have some ensemble of paths, of lattice paths on the plane. I have to specify exactly what paths are allowed, and I want probability distribution on those paths, and I want that probability distribution to have the following Gibbs property. I have my measure, I take some region on the plane, and I fix, that region, some paths are intersecting the boundaries, they are entering and they are exiting. So I take a region, and I fix the set of incoming points and the set of the outcoming points. And then I want that the conditional distribution given this information does not depend on what is going outside, but just what is the region and what are those points. And if this is the case, then I will call my measure, I then need to say more how the weights of the paths are arranged, but this is the Markov property, if you want, that I want to put. And in addition, I want to say exactly how this conditional distribution can be written down. So the definition is as follows: that I have to have some action function on the path, such that if I split the path in two, then the action is just the sum of those pieces. And then once I have such a function on paths, or on finite paths, if you want, then I can write down the probability distribution, in the conditional probability distribution, in the following way. I take my box lambda, and I take the set of the set of points where the paths are entering lambda, and the set where they are exiting. And I consider all the paths inside this box lambda which are connecting this set P from this and the set Q. And for every path in that family, I compute the action, and I add those actions. And this is my weight of the configuration of the paths. And then I just normalize, and this is the Gibbs distribution that I am interested in. Okay, well,
Paths are, you say the paths are self-avoiding, are also non-intersecting.
They are not intersecting, they are not even kissing, they are really self-avoiding in the strictest meaning of the word. And which paths are you getting, that depends on your kernel, and you should, and I will give you examples which we found, some examples. And but this definition, of course, is very general. You can put whatever you want. Then the question is for which kernels you will get something like that, and this is what I am going to explain. Okay. Now let me tell you what kernels we are able to study. The kernels, those matrix K, T prime, T double prime, we can treat. They are obtained in the following way. So those kernels are non-translation invariant. So we do it. We consider the following kernels. So we have our two-dimensional lattice, and for every column, the column has a number, the index k. So for every column, we pick up one of the following four functions. U is an argument, a complex argument, and those are just numbers, real numbers, constants. And okay, so for every column on the lattice, we fix one of those four functions, and we pick a corresponding constant. And then after having this family of functions, we define some kernel, which is a function of pairs which is a function of 2 points on the lattice. So this is the first point, this is the second, and we write down such integrals, complex integrals. And again, if you remember, there is this complex parameter which z, and this curve c is going from point z to the point z bar. And again, and you see that you have to pass by the origin from the positive side for half of those infinitely many integrals, and from the negative side for the other halves. So this is family of kernels that we are able to treat, and it so happens that for those kernels, so first of all, one has to check that this kernel indeed defines a probability measure. So, and this is some algebraic analytic computation that one has to do, and there is no way to avoid it, and no way to explain it easily why that situation gives rise to determinantal process. But in fact, there is much more general construction which still gets you a determinantal process, which means that all the determinants are between 0 and 1. But in this more general case, the fields are not Gibbsian. Only those members of that family turned out to give you nice from that point of view random fields. And now the fact is that if you take a random field which is given by this by those kernels that I'm talking about, and you take any configuration of that random field, the configuration of the random field is here depicted by red dots. Then with probability 1, what is true is that you really can construct a family of non-intersecting lattice paths. And this is again, okay, maybe I should backtrack. The reason for that is that the kernels that I wrote there, really they satisfy some linear relations of the kind that I showed you. I will not rewrite that linear relation. That will not tell you much by itself, but just the fact that there is this linear relation, that fact accounts for the fact that if I take any, with probability 1, any configuration of my random field, then what is true is that you can arrange, there is an algorithm which then to that configuration assigns a family of non-intersecting lattice paths. And as you see, those lattice paths, they are looking differently in different columns. So the first two columns, you see the paths are either horizontal or ascending by 1 unit. And that corresponds to the choice. So there are 4 options here. This is the first option, and here is the same one, see? Then those diagonal path can also be descending, like in that column. And then they can do something else. They jump, they go half unit this way, then they jump upwards, and then they go to the right. Or else they can go downwards, like in this column or in that column. And those 4 options, those are corresponding to the 4 choices of the elementary block by which you build up your determinant, this kernel. Okay, so depending on those 4 choices, you have 4 different behaviors of those paths. But the fact is that, well, knowing what was the choice of your kernel, you then can say that you can really associate to every configuration of your random field the collection, the algorithmically defined collection of random paths, of lattice random paths which are not intersecting. And
you're not going to generate every set of lattice paths this way, because in every column the steps are all of the same type, right? So there's a correlation between.
Well, definitely. The fact, what I'm saying is, take any configuration of your random field with probability 1. You even can see on that picture what is the algorithm to make it, and the statement is that with probability 1 it will work. So if you are in a beta plus column, that means you take a point and you connect, and then you take the next one, and then you have to find a guy either here or there to be connected. And also here you find one, and here you find one. Okay, and in the next column, for example, the rule is that you know that, so you have a guy here, and you know with probability 1 that before the next guy would appear here, somewhere here you will find a particle to connect to. So because from here you already have to start this way, so you know that with probability 1, somewhere here there will be somebody to connect that guy to. And the same here, see? Yes, so it's always like that, and that holds with probability 1. So the statement is that every configuration of your random field corresponds to a configuration of paths. Okay, and now I should tell you what are the weights for those paths. And the weights are simple. If for that case that we have this 3-line connector and it is upward, then the weight, that means that we are in a alpha plus column, and we have to count how many steps we make, and so the weight of that fragment is alpha plus 2 cube to the power 3. And here we go downward, and that means that we are in alpha minus column, and we make 2 steps, and this is the way that we assign to this piece of our path. And remember, my action is kind of summatory object, so I just need to know the function on a segment, and then I just multiply the weights, and that will give me a weight of a path. And for the remaining 2 ways of jumping up or down, the weights are again either beta plus or 1 over beta minus. So this is a fact. And then the statement is that if you take a kernel, which I showed you before, a few screens before, then the random field, the configuration of this random field can be interpreted as that picture was showing you, as a family of non-intersecting random paths. And this ensemble has Gibbs property in the sense that I described to you before. So you take a region, you fix the exit points and the entrance points, and then you compute the conditional distribution, and that conditional distribution is given by the Gibbs formula that I showed you, and the weights I already told you about, and the main result, what was behind our interest in that problem, is that the proof of those statements, to prove that you don't need the whole information about your kernel. Once you know that the kernel defines the probability distribution, this is hard to check, but the linear relations that you need in order that the theorem is to hold, that is not hard to check. And once those linear relations are holding, then the rest of that statement follows. So, and those kernels that I have shown you, they do have that property. Okay, and then I want, in the remaining time, discuss some examples of that kernels and some interesting measures that that one can get. So, what I call here beta paths are those kernels where at every column we make a choice, and well, the choice which is this alpha 1 plus beta to some u. This is maybe even I have on the next. Yes, this is the choice that we are going to use. So you see, we make for every k we take the function which enters into the definition of the kernel of the type 1 plus a constant time u, and that constant would depend on this value k. But let me go back to slides. So I just repeat what I said before. So those paths are paths which either go horizontally or they go at 45 degrees upward. So we have the collection of such paths, and then we can define the energy of a path. And I just repeat what I said before. So you have a path like that, which goes like this, something like this it is doing. And then how to compute the energy of such a path? You should do the following. You should draw the lowest lying path, which is also going this way, and you take this area, and this area is the relative energy of your path, and only those relative energies are needed in order to define for you the value of the action function, and then the measure, the conditional measure that you are getting, look really very similar. You can at least write it in a very similar way to the Gibbs formula. It is just the energy of the collection of the paths, and times the constant, which is here, should be interpreted as the temperature, and this is the choice of a kernel that we are making. Okay, so as you see, but it is easy to check that that the determinantal process that we are getting in this way, it is a process on a two-dimensional plane, and it is translation invariant in vertical direction and not translation invariant in horizontal direction. And in fact, here you see there is a real parameter kappa, and for every given kappa, the measure is different. So, so maybe there are some pictures I have to show you. Yes, yes. So, so there is this temperature in our model, and if we take temperature 0, then we're talking about ground state, what is called ground state in statistical mechanics. So for at this 0 temperature, the paths you would see, they just go for some time horizontally and then start off in a diagonal way. And your measure, the ground state measure, is just concentrated on such paths. And at low temperature, you just make some small perturbation of this picture. And this is a typical configuration of your random field of your paths at low temperature. So the fluctuations of those paths are just sitting in some strip of typically finite width, and only when temperature goes to infinity, those paths become this random field becomes translation invariant in two-dimensional translation invariant field, and this would be exactly those lozenges, tilings that I started from the very beginning. So one should think about those fields as deformation of this of the various translation invariant lozenge tiling fields, and maybe I just show you some more pictures, which then maybe where they are. Yes. So see if you then go back to pictures, and then this is how if you want to interpret your random field as a surface in three-dimensional space, then this is how it looks like. You have a stair here, which is going this way or horizontal, and then at a certain moment all the steps are making a corner. And so you should imagine the two staircases merging, okay? So I looked in the internet for a picture, for a similar picture, and this is the one you would find. So see, there are stairs on that side of the pyramid and stairs of this side, and then there is a corner where they merge together. And this is the random field that we are talking about here. So what is nice about this random field, as I told you, it is translation invariant in one dimension, and it is not translation invariant in the horizontal direction. Well, in statistical mechanics, we are accustomed to the fact that you can take a field and you shift it by one lattice unit to the right, and you get a new random field. This is very fine, but here but that gives you just a countable family of various measures which are different by a lattice shift. What happens here is something more interesting, that for any real shift, so to say, playing with this parameter kappa there. Okay, it already. Yes. Well, I made too many pictures for you. Yes, this parameter kappa here, if you change it continuously, then you are getting a continuous family of fields which are singular with respect to each other. So you remember that the tilings, in the tiling case, we had two-parameter family of fields which are classified by the tilt. Here, once you fix the tilt, you still have another parameter, and this is a parameter exactly where those two staircases are meeting. And you can move that point, in a sense, continuously, and therefore you are finding a whole continuum of ergodic fields which are mutually singular with respect to each other. This is what I wanted to say about those beta paths. And then you might ask yourself whether that shape here has an asymptotic shape. Well, for that you have to go to a limit of infinite temperature, so to say, because for a finite temperature, as I told you, the width where that configuration is not frozen is of a finite width only. So you have to increase that width. It should go to infinity, and then you should squeeze the things back, and then you would get a asymptotic shape for that surface. And it looks like some surface, some gutter shape. So those are straight lines. So it's a cylindrical surface, and then there is some curve which is responsible for the asymptotic shape. And that curve, okay, I will not be able to explain that in a simple terms, but there is a curve behind this picture which accounts for that asymptotic shape. And then my second and the last example is the case of another choice of my functions which then define my kernel. So I am alternating. I take at all even columns I take that weight for my kernel, and at every odd column I take this beta weight. So this is why I call those paths alpha beta paths. And in the same way as the beta paths are related to lozenge tilings, and this is easy to see how that relation goes, those paths that I'm talking about here, those are related to domino tilings. But to explain how you get from a collection of those alpha beta paths a domino tiling is a long story, and it is described in one paper of Kurt Johansson, but I will not give you the details, except I will show you later on some nice picture of that. And again, we have Gibbs ensemble of those alpha beta paths, and we can look how the ground state looks here and what the excitations about that ground state are. So this is a collection of this is a ground state configuration, and it is like that. So this is the position of the line k equals 0, and to the left of it, all the beta jumps are suppressed, and you can only go downwards. So you see those lines are going down, and remember they are not allowed to intersect. So once I have those positions here, then every guy tries to jump as low as possible, but he is not allowed to hit this guy here. So they are going down as much as possible, and then they turn right, and this is how they are working. And here they do not see any obstacles, so they go down, and we don't know what happens with them there. Okay, and from that position, the temperature suppress all those downward jumps, and only those upward jumps are left. So this is the beta jump that you go upward, and this alpha guy, in principle, he could have jumped this way, but this is forbidden by the energy. So they are frozen to go horizontally, and then they ascend. Okay, the nicest picture I have for you is what domino tiling corresponds to that picture of those paths. And here is the picture. And as you see, it is a bit, it requires a stress of imagination to believe that this picture encodes exactly that domino tiling of the plane. But this is the fact. So this is, in some sense, a ground state configuration for domino tilings. Namely, it is the ground state configuration in the following. The meaning of that statement is the following. Imagine you fix your domino tiling here on those two sides, and maybe also far away here and there. And then what you want to do is you want to minimize the number of places where you can make some move. Okay, in the lozenge tilings, the moves are what? You have 3 lozenges, and then you just flip them, which means that you add an extra cube. In the domino picture, the elementary move that you can do is to take a pair of dominoes and take them out and rotate them 90 degrees. And so that drawing here tells you what is the configuration where the number of locations which you can make your flip is minimal possible under the condition that you fix the boundary conditions. Okay, so this is the configuration, and again the same statement is true that so you have some measure on domino tilings. This is some new class of measures. It has one extra parameter in addition to what people usually consider, and therefore you are getting some non-translation invariant measures on domino tilings, which you can imagine how they look. If I tell you that this is a ground state, that means that the excited state is something which has well, those red squares not only here but in some vicinity of this thing, but they cannot go far away from that line. So the lower your temperature, the closer they are sitting to that line, so you get a non-translation invariant measure on domino tilings. And this is you get a flavor of how that measure, low temperature measure on domino tilings look like. And well, as I told you that we have a continuum of non-equivalent mutually singular measures on the domino tilings or on those alpha beta paths. And that brings me to the conclusion of my talk. So the conclusion is that the collection of kernels that I started with, that collection of kernels generates a determinantal random field which has this interlacing property of particles, which interlacing property then allows one to draw paths to interpret the configurations of that random field as a collection of non-intersecting random paths. Which kind of path depends on the model. As I told you, there are several options in our family. And then the measure that you are getting on that collection of random paths turns out to be Gibbs random path ensemble with some action functional, which is an additive functional and which allows you to write down the conditional distribution on the paths once you are given a region and you fix the exit and entrance points. And the main point and the main interest of ours was to understand how come that those kernels are generating families which have this locality property, and it turns out that a linear relation between the matrix element of this kernel, which looks like some kind of it looks to me like some harmonic condition that you just apply some difference lattice difference operator and you just get a delta function. This is the kind of the relation that I showed you. So that relation is behind the fact that this determinantal random field can be expressed, can have this locality property. So that's where I want to stop.
Any questions? Well, I have a question, I guess, about how you do these things, because enumeration of sets of non-intersecting lattice paths is kind of it's one of the standard techniques in enumerative combinatorics. And the way I learned it, it goes under the name of either Gessel-Viano method or Carlin-McGregor determinant or Lindström's lemma. Are these things that you use, or do you have another way of proving these things?
I would say my understanding is that it is completely different approach. So once you have this linear relation on the kernel, then you just see this locality property is some property of conditional distributions, right? You take what is it? The Gibbs property. You write down a conditional distribution in a box, and then you say, let me add one more point outside the box, and then you see that the conditional distribution actually does not depend on that point, right? So you have some identity, right? Now we're talking about determinantal fields. That means that we have an identity between some 4 determinants, which we have to check. Okay, and it turns out that nothing else is needed to check that but that linear relation that we have. So this is the way. Once you guess what is the reason for this locality property, you just go and you, with brute force, you just write down all those big determinants, and you look at them for some time, and then you see, yes, that those linear relations, they generate, well, infinite families of identities between determinants of various size, and those identities is in the collection of all of them is the Markov property, is this locality of the Gibbs field property. So we don't have to enumerate paths here. We just want to have a bijection between the random field and the path, and to see that the measure that we are getting there is the lattice measure. So we are not trying to answer questions about the properties of those measures, except for the fact that they have this Gibbs property.
I guess, from my point of view, once you know that your random field has this interpretation in terms of non-intersecting lattice paths, it's kind of automatically a determinantal field because of the Carlin-McGregor Gesell-Viennot determinant formula for non-intersecting lattice paths.
Well, first of all, we have weights here on the paths.
Yeah, that's okay.
That's okay. And then we have different paths, as you say. And this is also okay?
I think so. As long as you put the weights on the paths properly, these determinantal formulas should still apply. Yeah.
Mm-hmm. Is it correct that the measures that you are getting in that way are Gibbs measures?
Yeah. I mean that follows from what you said about the action being sort of independent on a concatenation of 2 paths.
Mm-hmm, mm-hmm,
and you get the Gibbs thing as well.
Mm-hmm. And are those kernels look familiar to you?
No, actually, I've never seen those kernels before,
Mm-hmm.
except those 4 parameters that you have, the alpha plus
Mm-hmm.
and minus, beta
Mm-hmm.
plus and minus. That looks a lot like entire functions of Poier-Laguerre class 1, and that comes up in this theory too, with total positive matrices,
Mm-hmm. Mm-hmm.
Carlin-McGregor determinants.
Mm-hmm.
So, well, we should talk about this.
I will be very happy to. Yes. Thank you.
Okay, I guess that's it.
Thank you.
Let's play soccer.